Hello everyone, my name is Justin Morris and I'm a PhD student at the University of California, San Diego and San Diego State University. And today I will be presenting our work, HyperSpike, Hyperdimensional Computing for More Efficient and Robust Spiking Neural Networks. I'll first start off with a bit of motivation. Here we see an example of recent work in machine learning where Google's AlphaGo was able to beat the best Go player in the world, Lee Sedol. However, the problem is Google's AlphaGo is extremely energy intensive, costing 1 megawatt of energy to run with 2,000 CPU cores and 300 GPUs. It also took a team of 100 scientists to create it. On the other hand, Lee Sedol's brain takes about 20 watts to operate, and his whole body takes around 100 watts. And all he needs is a little bit of food or drink to provide his body with energy needed to play Go. From the prior slide, it's clear that we need to take more motivation from how the human brain operates in order to achieve more efficient machine learning solutions. That's where neuromorphic computing comes in. In neuromorphic computing, we try to emulate the brain's physical processing in hardware. In this paper, we go over two different neuromorphic algorithms and combine them together, spiking neural networks and hyperdimensional computing. The first algorithm we will talk about is spiking neural networks. These networks operate on event-based data where only the differences between the previous frame and the current frame are fed into the network. The neurons in the spiking layers then accumulate these differences and output a spike when a threshold of activity is met. Spiking neural networks are also constructed similarly to deep neural networks, as you can see in the figure, in which the first few layers can perform convolution operations. Then later layers are connected neurons that eventually end in an output layer, where the prediction is made. Hyperdimensional computing is a lightweight machine learning algorithm designed after the sparse distributed memory model of the brain. HD computing works by first taking all of the samples belonging to a single class and encoding them to high dimensional space, where D is 10,000. We call these hypervectors. Then we combine all of the samples belonging to a class together to create one hypervector representing the class. Then we do the same for the rest of the classes. In this case, we have cats and dogs. Now we have a model with which we can use for inference. To perform inference, we first encode the sample image into a hypervector using the same encoding used during training. Then we perform a similarity check to find the most similar class hypervector, and the most similar one is chosen as the output. The similarity check performed can depend on the data type of the dimensions of the hypervectors. For instance, in this work, our hypervectors are binary, therefore we can use a simple Hamming distance check to count the number of mismatches. However, for integers or floating point values, cosine similarity or dot product may be used instead. There has been numerous works expanding on spiking neural networks. For example, surrogate gradient learning in spiking neural networks expands on the training of SNNs. There has also been work on combining HD with other classifiers to improve their energy efficiency. For example, hyperdimensional computing for efficient distributed classification with randomized neural networks combines HD computing with a random MLP for more efficient classification than a deep neural network. Furthermore, there has been work combining SNNs and HD recently. However, this work differs from ours as they simply use a LIF layer instead of a convolutional layer for the SNN. And we also evaluate the robust properties of HD in more detail. SNNs and HD computing have different pros and cons. For example, SNNs have the ability to process event-based data from neuromorphic sensors. However, they are more energy intensive and not as robust to errors. HDC has simple, highly parallel operations that make it more energy efficient. Since information is evenly distributed in high-dimensional space, operations are also more robust to errors. However, hyperdimensional computing cannot natively process event-based data. By combining both of these approaches, we create HyperSpike, which takes the pros of both SNNs and HDC and tries to eliminate the cons. HyperSpike starts processing with the SNN. Our baseline SNN architecture starts with a convolutional layer and ends with an MLP as a classifier. However, with HyperSpike, we only need the SNN to convert the event-based data into a more traditional feature vector that hyperdimensional computing can interpret. So we just take the first convolutional layer of the SNN and remove the rest to be replaced by hyperdimensional computing. We additionally are able to use random weights for the convolutional layer and do not need to perform training on it. After the SNN convolutional layer processes the event-based data, HDC then encodes that output into a hypervector using our random projection-based encoding. Next, that hypervector is then put through HD training, where it is added to the class hypervector that it belongs to. We do this for every sample to obtain our HD model. This HD model can now be used for inference. To perform inference, we follow the same pipeline. However, instead of going to the training block, the encoded hypervector is compared to the class hypervectors, and the most similar class hypervector is chosen as the output. Here we compare using an SNN with a more traditional MLP output layer with random weights and a varying amount of layers with HyperSpike under the same conditions. The y-axis is the accuracy of the NMNIST dataset, and random is with random SNN weights, and trained is with pre-trained SNN weights. As the data shows, HyperSpike is not only able to utilize just one SNN layer and achieve similar accuracy, but also does not need to train that SNN layer and can use the random weights. Here we show how the output of the convolutional SNN layer is encoded into a hypervector. We first generate a random projection matrix where each element is uniformly randomly selected to be +1 or -1. The size of this matrix is d by n, where d is the desired dimensionality and n is the size of the output from the convolutional layer. Then by matrix multiplying this matrix with the output vector, seen as f here, we get a new d-dimensional vector that is the encoded hypervector. To go over how we train the binary HD model in HyperSpike, I will first go over the baseline HD retraining. We first encode the training sample into a hypervector using the same encoding used during the initial training. Then we perform inference on that sample to classify it. If it was a correct match, then no update is needed. However, let's say it was an incorrect match. In this case, we incorrectly classified it as class 2 when it was supposed to belong to class 4. Then we have to subtract the query from the wrongly classified vector and add it to the correct one. This makes the correct one more similar to the query and the incorrect class less similar. And by doing this over all of the samples for multiple iterations, we can stabilize to a more accurate model. Quantized retraining is similar to the baseline retraining method. We first encode the training sample into a hypervector using the same encoding used during the initial training like before. Then we perform inference on that sample to classify it. And again, if it was a correct match, then no update is needed. However, we need to update the model if it was an incorrect match. In this case, we again are saying that our model incorrectly classified the sample as class 2 when it belongs to class 4. But we cannot simply modify our quantized class hypervectors like we do in baseline HD, because this would result in drastic changes to the model, especially since we quantize 2 binary values in this work. To get around this, we keep the floating point model around and perform the update on the floating point model, then update the binary HD model by re-quantizing the floating point model. And the way that we quantize to binary is we simply take the sign bit of each dimension, and we make any positive number a +1 and any negative or 0 number a -1. Then our class hypervectors are binary, and we can do a simple Hamming distance check between the classes and the query. And by modifying the floating point model and then requantizing every time, this allows for finer adjustments to the quantized HD model, rather than trying to modify the binary model or quantized model directly. And this retraining method can work for all types of quantization methods. It does not have to just be binary. In this work, we also analyze the robustness of HDC to bit error rates in memory. We assume all of the weights are stored in memory and subject to errors. This includes the SNN weights, random projection matrix, and hyperdimensional computing hypervectors after encoding. Since bit error rates vary greatly between memory technology and operating conditions, we do a wide sweep of bit error rates from 10 to the -5 all the way to 0.5. For our experimental setup, we verify the functionality of HyperSpike using both software and hardware. We implement HyperSpike with Python using a C++ backend for training and inference. For hardware, we estimate the SNN convolution energy execution time and area using Intel's Low-E heat chip. For hyperdimensional computing, we utilize the architecture provided by TinyHD, and again use that to estimate energy execution time and area for the HD part. We also experimentally show that hyperdimensional computing is highly robust to errors by simulating bit flips in our Python software. We test HyperSpike on 3 popular vision-based event-driven datasets: NMNIST, DVS gesture, and ASL DVS, where NMNIST is digits, DVS gesture is hand gestures, and then ASL DVS is American Sign Language. And all of these datasets are vision-based event datasets. Here we see the impact of bit error rates on the accuracy of the models. We have 3 models that we compare to: HyperSpike, a baseline SNN with an MLP classifier, and an SNN with a VAE classifier, where VAE is a variational autoencoder. As the results show, HyperSpike is able to achieve similar accuracy to the other models when there are essentially no bit errors. Furthermore, as the bit error increases on the x-axis, HyperSpike is able to maintain accuracy for higher bit error rates than the other classifiers. This is due to a combination of high dimensionality with the hypervectors and the binary representation used for those hypervectors in HyperSpike. Because the other models are using 16-bit quantized values for all of their weights, every bit flip is disproportionately incurring more error than a bit flip in HyperSpike, because every single bit flip in HyperSpike is equally incurring the same amount of error. But depending on which bit you flip in the SNN MLP or SNN VAE, they can have different varying amounts of error incurred. For example, if you flip a lower bit, it's not as much error, but if you flip the most significant bit, then there's a lot of error that's added in the other models. Overall, HyperSpike is 31 times more robust to errors than the baseline SNN, which is the SNN and MLP. And this means that at a typical error rate being 0.1%, HyperSpike loses 31 times less accuracy than the SNN. Here we evaluate the impact of dimensionality on the robustness of HyperSpike. We show two different scenarios. The first in blue is a more typical bit error rate of 0.1%. The second is an extreme case of 3.4% bit error rate in red. As the curves show, the higher dimensionality HyperSpike has, the more robust it is to errors. This is because the information can be spread more evenly across higher dimensionality. Thus, each bit flip is less amount of error. This matches previous results shown in other papers. Here we compare the energy, execution time, and area of HyperSpike to our baseline SNN. Note that the y-axis are in log scale, so the differences are larger than they appear. But as the graphs show, HyperSpike is 2.6 times more energy efficient and achieves a speed up of 10 times over the traditional SNNs. HyperSpike is also 3.4 times smaller than a traditional SNN running low-EHE because we only use the first layer and also use the smaller HyperDimensional computing as our classifier. So in conclusion, HyperDimensional computing is a promising lightweight classifier for more energy efficient learning and is also robust to bit error rates in hardware. And we show this experimentally in our paper. HD computing is unable to natively classify event-based signals from neuromorphic sensors. However, by using a single random convolutional layer from an SNN to extract features from the DVS data from the neuromorphic sensors, HD can provide more efficient and robust classification compared to traditional SNNs. And overall, HyperSpike is 2.6 times more energy efficient, achieves a speed up of 10 times over traditional SNNs, and is 31 times more robust to bit error rates at a bit error rate of 0.1%. Thank you for listening to this talk. Here are some references that we refer to in the paper. That is all. Thank you again.